the title of my talk is The Economics of Unknown Unknowns, and to get you thinking about these things.
There are known knowns. There are things we know. And we also know there are known unknowns. That is to say, we know there's some things we do not know. But there are also unknown unknowns. The ones we don't know, we don't know.
So that was former US, I need to maximize this. There. Is that on full screen? Here. All right. So that was Donald Rumsfeld, former US Secretary of Defense in a US Department of Defense news briefing from 2012 about the lack of evidence linking the government of Iraq with the supply of weapons of mass destruction to terrorist groups. And you notice that he mentioned these three things: known knowns, known unknowns, and unknown unknowns. And what I'll talk about today is how do economic models deal with each of these. So before I do that, I want to tell you some general things about decision theory, which is my field of research. So an agent, an economic agent, is characterized by his or her preferences, captured by the preference relation squiggle wiggle. And this preference relation makes pairwise comparisons between the agent's objects of choice. For example, abstractly, we can have X is at least as good as Y, or based on my experience from last night, a vacation to Jamaica is preferred over a vacation in Houston. I don't know if you know, but I just got in like this moment. So, but anyway, you take two bundles and you compare them. That's what the preference relation does. All right. It's very inconvenient to work directly with preference relations. If you think about the standard consumer's problem of choosing the best bundle in their budget set, right? The budget set contains an infinite number of bundles, meaning you would have to do an infinite number of pairwise comparisons, which is obviously very impractical. It's a lot more convenient to work with utility functions, which you probably do all the time, right? Because there we have some nice, very useful, convenient tools available. We can take the utility function and maximize it over the consumer's budget set, for example. Okay, so here's the thing that you may not think about when you're doing that using a particular utility function is equivalent to making a specific set of assumptions that we refer to as axioms about the agent's preference relation. Right? And what decision theory does, it makes the connections between these axioms or assumptions that about the preferences and the properties of the utility function, so that when we use a particular utility function, we know what we're implicitly assuming about the agent's preferences. Or in the other direction, if you can accept the assumptions about preferences, then you should be comfortable working with this utility function. Okay, so with that being said, let's move to the first of the concepts that Donald Rumsfeld was talking about, the known knowns. And this is choice under certainty, where the future outcome is certain. And an example you've probably seen in your classes is the Robinson Crusoe economy, where we have a single individual. So the individual has nobody to trade with. And we have 2 points in time, now, and which is t equals to 0, and the future t equals 1. There's one non-perishable good. So since it's Robinson Crusoe, let's think about it as coconuts. And Robinson Crusoe has an initial endowment of capital X coconuts at time 0 and a future endowment capital Y coconuts at time 1. So what is the problem we're interested in? So Robinson has to choose how to allocate his consumption across time. We let little x denote his consumption now and little y denote his consumption in the future. And we assume that Robinson's preferences are characterized by a utility function u of the consumption now and future consumption, with the partial derivatives being positive. So his utility is increasing in both consumption now and future consumption, and it's strictly concave. So what are the constraints that Robinson is facing? Well, first of all, his current consumption cannot be any larger than his endowment, his current endowment. Right? Second, he could take the coconuts he has today and save them for tomorrow. So his future consumption is constrained by the total amount of coconuts today and tomorrow. But then any coconut he eats today is not available to eat tomorrow. So we also have the constraint that his future consumption has to be less or equal than future endowment plus today's endowment minus whatever he eats today. Okay, so now we know everything we need to know. We know who the agent is and what the agent's objective is. We know what he's choosing. And we know which constraints the agent is facing. So now we can go ahead and solve this problem. Because utility is increasing, the budget constraint, or the constraint 1, will hold with equality. That's nice because then we can simply plug it into the utility function. And we can take the derivative with respect to x, set the derivative equal to 0, and that gives us that this result that the marginal utility with respect to x divided by the marginal utility with respect to y evaluated at the optimum equals 1. This is simply this example's version of the well-known marginal rate of substitution equals the price ratio. The price ratio is 1 because if you give up 1 unit of consumption today or 1 coconut, you get 1 extra unit of consumption tomorrow. Right? So 1 extra coconut tomorrow. In a figure, right, we have the constraint set in black. Right? We can eat no more than x today. We can never eat no more than y plus x tomorrow. And we have this trade-off, a budget line of slope minus 1, because, as I said, if we eat a coconut today, we cannot eat that tomorrow. And then what the condition marginal rate of substitution equals the price ratio gives is the slope of the indifference curve equals the slope of the budget constraint. In other words, this is the highest difference curve we can get to that's tangent to the budget set, and that's what we want, right? The objective is to maximize utility, get to the most preferred bundle. So we see that existing economic theory does very well with the known knowns with choice under certainty, right? We can easily analyze a lot of problems where we have certainty. Okay. Let's move to the known unknowns. This is choice or decisions under uncertainty. So now the future outcome is not certain. For simplicity, we'll still just consider 2 points in time, now and the future, 0 and 1. Decisions are made at time 0, and when decisions are made, the agent is not sure of the future conditions or outcomes or payoffs. And we model this uncertainty with what's called the state space, which is a list of every possible relevant resolution of uncertainty. Right? So, in other words, this capital S is a list or a set of everything that can possibly happen. Right? So, for example, if I'm an umbrella seller on the streets of New York, relevant states may be sun and rain for my decision. That's one example. Each state Sj occurs with probability pi j. Right? So, for example, we can have a situation where the probability of sun equals the probability of rain, both being equal to 1/2. Right. What is key is that future consumption is now a random variable. So it's a vector of possible consumptions at time 1. Right? So you can also think of it as a contingent plan. Y1 is the consumption I will consume if state 1 occurs. Y2 is the consumption I will consume if state 2 occurs, and so forth. Right? So there is uncertainty, but we can describe it very precisely. Right? We can describe what the states are. We have these probabilities of the state, and we can talk about the consumption in different states. Now, preferences over future consumption are characterized by an expected utility function. So if I consume yj in state j, I derive a utility u of yj in that state. I get a utility in that state. And then I multiply that utility for the state with the probability of the state. And then I sum over all the states to get this expectation of my utility, the expected utility of the consumption vector y. Right? So in our example, if this utility function u is equal to square root of yi, then our expected utility of the consumption vector y would be 1/2 times the square root of y1 plus 1/2 times the square root of y2. Yes?
With regards to the probabilities, are we using discrete or continuous?
You can use both. Right now in my examples here, I'm using discrete, but there's certainly also models where they're continuous. Yes. Other questions at this point? Okay. So let's see an example of how this plays out in an economic problem. And here I'm considering an investment problem where we have an investor who lives in an economy with one non-perishable physical good. And there are two possible states of the world at time 1, S1 and S2. Now there are two assets available that this investor can invest in. Asset 1 costs 3 units of the physical goods today. It pays 5 units in state 1 and 1 unit in state 2. The other asset 2 costs 2 units of the physical good today, pays 3 units in state 1 and 1 unit in state 2. And our investor is endowed with 50 units of the physical good today. He'll receive 2 units in state 1 and 1 unit in state S2. Right? And he has utility represented by the expected utility function I just showed you, 1/2 square root y1 plus 1/2 square root y2. Okay. So the problem I'm interested in is forming the investor's optimal portfolio. How much should he buy of each of these two assets in order to get to the best possible consumption combination in the future? And I let theta 1 denote the amount he buys of asset 1 and theta 2 denote the amount he buys of asset. So theta 1 is the amount he buys of asset 1 and theta 2 is the amount he buys of asset 2. So theta is his portfolio. Right, so as usual, we have to think about who is the agent, what's the agent's objective, and which constraint is the agent facing. So his budget constraint at time 0 is, well, think about it, he only derives utility from consumption at time 1. So he will spend all his money today buying the two assets in order to get as much consumption in the future as he can. And so he has $50, and each unit he buys of asset 1 costs 3. Each unit he buys of asset 2 costs 2. So we end up with this budget constraint. We also have to think about what are the time 1 consumption levels as functions of the portfolio he forms. Remember, asset 1 pays off 5 units in state 1, asset 2 pays off 3 units in state 2, and he has asset 1 pays off 5 units in state 1, asset 2 pays off 3 units in state 1, and he's endowed with 2 units in state 1. So the top line is his consumption in state 1 when he has the portfolio theta. And the bottom line is similarly computed as his consumption in state 2 given portfolio theta. Okay. So we can plug these consumption levels as functions of the portfolio into our utility function. That's what I've done down here, right? And we are maximizing that utility function by choosing the appropriate theta portfolio subject to the investor's budget constraint. We can set up the Lagrangian for the problem, take the first order conditions, the derivatives, partial derivatives with respect to theta 1 and theta 2, set them equal to 0. Now we have 3 equations. Here we have the budget constraint, we have these 2 equations. And when we manipulate them, we get that theta 1 is equal to minus 51, and theta 2 is equal to 101.5. So the solution to the investor's problem is to buy 101.5 units of asset 2 and sell short 51 units of asset 1.
But this is assuming that the investor is aware of the probability of the 2 different states, right?
It's assuming a lot of things. It's assuming that he knows the probabilities of the 2 states, or at least has some. I mean, so I'll get to this in a second, but it doesn't have to be exogenously given probabilities. We can actually often derive the probabilities from his preferences, like as long as he has some in his mind that how likely he thinks the 2 states are. We can do this exercise. But it's also assuming, of course, he knows what the 2 future states are, right? That are not no more than 2 future states, right? So he needs to know that exactly what the situation he is in is, right?
To what extent do you have to account for like really bad version in this kind of a problem? Like if I really don't like really bad states of the world versus I'm kind of indifferent to somewhat good states of the world.
Good. So in the expected utility model, the investor or the decision maker's risk attitude is captured by the function little u. So that will capture his risk attitude.
Okay.
And in the standard model that most people work with, which is the one I showed you, utility is independent of state. This little u does not have a subscript s, if you notice that, right? So that's the standard model that most applied people use, and the implicit assumption there is that the utility function is the same in all states. Right?
Okay.
And also here, as I answered your colleague, we assume in the model that the decision maker knows in advance what are all the relevant states, right? So that we can do this exercise, we can compute this expected utility. Did I answer both your questions? Okay, good. So, but with those things in mind, we see that the standard theory does quite well in solving problems with known unknowns, right? If we can formulate the problem fully, right, we have a powerful tool, expected utility, that we can use to analyze these models. Okay, so one more thing I want to talk about is information in this model, in the expected utility model. So how is the arrival of information, new information model? Well, when the agent receives new information, it narrows down the list of things that can possibly happen. So remember, we start out with this state space, right? And what happens when the agent gets more information is it rules out some states. So in some sense, you can say the agent's knowledge becomes more precise over time. Right? And when that happens, when we're ruling out some states, the prior probabilities, the probabilities that we start out with, are updated to form posterior probability using Bayes' rule. And I've written Bayes' rule here, right? The probability of A given event B, given that you know event B is the true one, is the probability of A intersect B divided by the probability of B. So what Bayes' rule does in words is it takes probability mass from the ruled out states and redistributes it proportionately across the remaining states. And another feature of the expected utility model is that the utility function little u remains unchanged, right? So when we get new information, it materializes in the decision maker's preferences by updating his or her probabilities assigned to different states. But the tastes per se remain unchanged. Here's an example where the agent starts out with a prior state space consisting of 4 states. And the probabilities of these states are 1/7, 2/7, 1/7, and 3/7 respectively. Now the information gets information that the state is not S3. Right? So he or she will update the probabilities of the remaining states using Bayes' rule. How do we do that? Well, what is the remaining event that is not ruled out? That is the event consisting of states S1, S2, and S4. Right? So we take each probability of this, to get the probability, the posterior probability of state 1, we take 1/7 and divide it by the probability of the event that's left, right? Probability of state 1 plus probability of state 2 plus probability of state 4 gives us 1/6. And we do the same for the probability of state 2 and for the probability of state 4, giving 1/3 and 1/2 respectively. And the ruled out state gets assigned probability 0, right? So as I say, we've taken the probability of state 3 and redistributed it on the remaining states. Something I would like you to notice is the relative probabilities between the remaining states. So if you look at state 1 and 2, for example, like the relative probability of state 1 to the probability of state 2 is 1/2. That is still the case after they've been updated. And similarly, the relative probability between state 1 and state 4, for example, is 1/3 in the prior. And we have that same relationship in the posterior, right? So 2 things. We take this probability mass and shift it away proportionately. Sorry, we take the probability mass of the state we ruled out and distribute proportionally across the remaining states, and by doing that, the relative probabilities of the states that remain is the same as it was before. Okay. Some general comments about this expected utility model, right? As I mentioned earlier, when we have a specific functional form of the utility function, here expected utility, it's equivalent to making a specific set of assumptions about the preferences of the agent, and here this set of assumptions is called, maybe not surprising, the expected utility axioms. Another thing that we talked about is with expected utility, you can separate the agent's tastes that are captured by this function little u from her beliefs that are captured by the probabilities. To get back to your question, right, the probabilities can be objectively given, or they can be subjective, so derived from the agent's preferences. They could be just, you may think that the probability, there's a particular probability that a particular stock has a higher value tomorrow than it does today, and the person next to you may have a different subjective probability of that. Right? But in principle, with the tools from decision theory, we can derive that even when the decision maker doesn't know the objective probabilities, if we have a particular set of axioms that we're willing to accept, he acts as if he had particular subjective probabilities. So the expected utility model is broadly applicable. One more thing is the state space is exhaustive and fixed. As I showed you with the information arrival, right, we start out with this list of everything that can possibly happen, and then when we get information, it just narrows down the list. Right? So in this expected utility model, the model of known unknowns, the economic agents never discover new things that expand the universe. Right? Knowledge never truly grows. Right? When you get information, things become more precise, but knowledge never grows. Okay, so this was always unsatisfactory to me. Experience and intuition alike contradict that agents never discover new things, right? Both history and our own lives include occasions where we become accustomed to new possibilities that were once inconceivable, right? And presumably this fact that we realize this affects the decisions we make, right? So there seems to be an important feature that the economic models should be able to take into account. I have some examples, right? National defense could be new strategies of terrorists that governments haven't taken into account. In industrial organizations, it could be your competitors inventing new products that you don't know what are. And from our own lives, it can be growing up, right? Children don't envision everything they'll encounter in their future lives, right? Or as one of my referees put it, the Bayesian baby whose first words are not mama, but this complete list of everything that can possibly happen in its life doesn't exist, right? So I'm thanking the anonymous referee for that one. My point is our universe frequently expands as we become aware of new opportunities, right? And our economic models should be able to handle this. Right. So this is what I've done in my research with, the first couple of papers with Adi Carney from Johns Hopkins University. So the paper I'm going to talk about now is called Reverse Bayesianism, a choice-based theory of growing awareness, which we published in American Economic Review in 2013. Right? And in our model, we have a model of exactly this case where the agents can make discoveries over time that expand their awareness. And the two main issues in dealing with this, the first is to provide a framework to model increasing awareness, because that's not possible within the standard state space model. And the second is to figure out what is the behavior in response to growing awareness. Like how do we model behavior when this happens? So in our approach, the state space expands as the agent's awareness increases. And we provide a list of axioms, a set of assumptions about the agent's preferences in this expanding universe. And if you accept our axioms, you get that both how the agent behaves for a given level of awareness, and also how the agent responds when his awareness increases. So you get both of those two things out of the utility representation we have. So here, let me give you a preview of our results. In the framework, there are two different types of discoveries that the agent can make, and they materialize differently in the expansion of the state space. But in either case, we end up with more states than we had in the beginning. In one case, we add new states to the prior state space. In the other case, we split the old states, so we get a finer partition of the state space. In terms of behavior, we get representation theorems. So what does the utility function look like for each particular level of awareness? And then we get rules for updating beliefs over the expanding state spaces. So for a given level of awareness, the decision maker is an expected utility maximizer. And then when the state space expands, the evolution of beliefs happen according to what we call reverse Bayesianism. Now, why did we choose that name? That's because with our updating rule, probability masses shifted proportionately away from events in the prior state space to events that are created as a result of this expansion of the state space. And we preserve the relative probabilities of the prior known states. So if you think about it, it's the exact opposite of Bayes' rule, right? When we're going in the opposite direction of expanding the universe, of adding more states. And that's why we chose that name. Okay, so the two types of discoveries that we're considering, they are discoveries of new consequences. So here an example is the discovery of the New World when Columbus sailed west, right? I think he and the crew anticipated finding India or sailing over the edge of the world. Presumably they did not anticipate finding a new continent. And the other example, or the other types of new discoveries that we consider, is the discovery of new feasible acts or actions. One example here is the invention of sound recording that creates the probability of reproducing current sounds in the future. Another example is the invention of financial instruments such as options that creates new probabilities of, or new possibilities of hedging your investments, right? That weren't there before. Okay, so let me show you the model. And I'm trying to be non-technical here, but I still need a little bit of notation. So we start out with a finite non-empty set F of feasible actions. So these are the different actions that the agent has available that he knows of, that he can take. And then we have a finite non-empty set C of feasible consequences, which are the things he directly cares about that are going to result from the actions. So think back to the sort of the known model of known knowns and model of unknown unknowns, right? The agent there cared about his consumption, right? So that would be a consequence would be what consumption do I get to take, or which vacation do I get to go on, or something like that, right? And the action would be the action of buying a particular portfolio, right? That then results in a particular set of consumptions. Okay. So what we do now, from these two sets, the set of feasible action and the set of feasible consequences, we define what we call a conceivable state space as the set of all the mappings of functions from the set of feasible actions to the set of consequences. This sounds very abstract, so let me give you an example. Here's an example where our agent knows of two feasible actions, F1 and F2, and of two feasible consequences. So what is the state space? Well, it's all the possible combinations of assigning the two consequences to the two actions, right? So in that way, it's all the possible resolutions of uncertainty, right? So one possibility is that both actions could result in consequence C1. We call that state 1. That's one possible resolution of uncertainty. Then there's a different possibility that the first action could give C2 and the second action could give C1. That's the second possibility. Third possibility is the first action could result in C1, the second action could result in C2. And the final possibility is that they could both result in consequence C2. And now there are no more possibilities. I've exhausted all the possible ways that we can assign two consequences to two actions. So this is my conceivable state space. This is the maximum amount of uncertainties that I can express given my awareness of two actions and two consequences. Right? There's no more uncertainty that I could possibly describe. And that means that in our model here, a state is exactly just an abstract notion of the resolution of uncertainty. We no longer have that physical description as I did in my example before with the sun and the rain, right? Because here I'm just saying simply a state is one possible combination we could resolve uncertainty. All right. So now the question is, how do the two types of discoveries materialize in the evolution of the state space? So we start out in the same situation as I just described, with the two actions and the two consequences resulting in four states. And now we discover a new consequence, C3. So now, after this discovery, the set of known feasible consequences is C1, C2, C3. So what happens to the state space? Well, now we also have to consider that each of the two actions could result in this consequence C3. So we have first the same four states as before. Right? But then we have 5 more states that involves combining C3 with the other two consequences and itself in all the possible ways we can do that. Right? So we see that when we discover a new consequence, we add points to the state space, right? The state space expands. We have more states now. What happens if we instead discover a new feasible action? So we start with the same starting point, 2 actions, 2 consequences, and now we discover a new action. So now we have 3 actions. And what happens to the state space? Now a state has to tell us not only which consequence the first 2 actions result in, but also which consequence the third action results in. So the length of the description of a state is now larger, right? We need 3 components to describe a state. And if you notice, the old state is 1. The one that we called this one before, which was C1, C1, right, is now split into the states S1 and S5, right? In both those states, we have the first action gives C1, the second action also gives C1, but then there are two possibilities, right? The third action could give C1, or the third action could result in C2, right? So, and the same can be said for all the other prior states, right? So when we discover a new action, it materializes in the evolution of the state space by splitting each of the existing states. In either case, whether we discover a new consequence, a new action, we have more states now than we did before, but they materialize in different ways. Yes. All right. So that is the framework. And now let's move to the objects of choice. What is it that the decision maker is choosing between? Well, there's a standard in decision theory that we call the objects of choice acts. Acts are functions from states to consequences, or technically speaking in our paper, they're functions from states to lotteries over consequences, but I'll try to avoid talking about that because it just complicates things intuitively. So what do I mean by that? The acts being functions from states to consequences. I mean that for each state, an act results in a particular consequence, right? So think back to the portfolio. If I choose the portfolio theta1, theta2, I get particular consumptions y1 and y2, right? So that is a function from the act of choosing the portfolio theta1, theta2 to consequences. One consequence, y1 for state 1, and one different consequence, y2 for state 2. Right? So here is an example, like 4 states, 2 possible consequences. An example of an act is lowercase f, that if state 2 occurs, the act returns consequence C1 to me. If any of the other states occurs, the act returns consequence C2, or pays me consequence C2. All right. And these acts, the set of all such acts, is what the decision maker has preferences over. Those are the objects of choice, right? So it's an abstract model, so the decision maker is walking around choosing between different such f's, right? And that's also what he or she has preferences over. In this world with growing awareness, you notice that we have different state spaces of different dimensions, right? So in the prior state space, an act F tells me what do I get in each of the 4 states, right? If I discover a new consequence, an act will tell me what happens in each of the 9 states, right? So we need axioms and preferences within each level of awareness, and then we also need axioms that connect preferences across these different levels of awareness, right? Because they live on different domains. So let's start with the axioms that we impose for each level of awareness. Squiggle wiggle, the preference relation is assumed to satisfy the expected utility axiom, so subjective expected utility axioms. So the subjective expected utility axioms are the ones that allow us to extract the decision maker's beliefs over states from his or her preferences. And they are, you've probably seen the first 2, I would think, because they're the ones that guarantee existence of a utility function at all. A weak order, squiggle wiggle, is transitive and complete. And second, that we have an Archimedean continuity axiom that says that small changes in the consumption bundles only changes your utility a little bit. Then we have an independence axiom. That's basically saying that if for some bizarre reason you would prefer $100 over a picture of my children, then you would also prefer a 50-50 lottery of coin flip between the $100 and a sweater over a 50-50 coin flip of the picture of my children in the sweater, right? So if you're mixing the same thing in with the same probability, you preserve the preferences. Did you have a question?
No, sorry.
Okay, so then we have monotonicity that says if something is preferred in all states, then one act gives you something preferred in all states, then another act, then you prefer the former act. And finally, non-triviality says simply that there's something the decision maker cares about. So those were the axioms that we imposed for each level of awareness. Now let us move to the ones that are connecting preferences across different levels of awareness. The first one we call invariant risk preferences. And it requires that the decision maker's attitude towards prior known risk is independent of his awareness level. So that the part I would like you to focus on is this prior known risks. So risks means that we are looking at acts that have no variability across states. So we are removing anything subjective from them. We're just looking at acts that give you the same in each state. And known risks mean that it's when we're looking at consequences that we were aware of before. And then we say, okay, even when awareness increases, you don't change how you feel about the consequences you knew before, right? As long as they're only involving risk and no subjective uncertainty. This second, we need one more axiom in each case. When we deal with the discovery of new consequences, we add an axiom that we call awareness consistency. And that requires that the agent's preferences conditional on the prior state space are unaffected as awareness grows. So if you can think about again, the before acts, think to the examples, right? Live on 4 states, tell us what do we get in each of the 4 states. And then after we've made the new discovery, the acts will tell us what happens, what do we get in each of the 9 states, right? And if beforehand you had one act that was preferred over another, and now you have 2 new acts where they give you the same in the new states, so you really don't have to worry about what happens in the new states because there they give you the same. And then they agree with the old acts on the old state space, then your ranking would be the same, right? That's another more detailed way of saying what is stated on the slide, that the agent's preference is conditional on the prior state space are unaffected as awareness grows. When we're dealing with the discovery of new actions, we instead add an axiom called projection consistency, which is similar in spirit to awareness consistency, but because the discovery materializes differently in the evolution of the state space, we just need some different details. All right, so let's see what we get out of these axioms. So the axioms are equivalent to the following utility representation and updating of beliefs. So we get that for each level of awareness, the decision maker is an expected utility maximizer. So what are the parts here? Well, the f of s is what the act gives us in state s, what act f gives us in state s. ui is the utility of the act in state s. The utility, also called Bernoulli utility of the act. and then we have subjective beliefs over the states, and we form a expected utility, subjective expected utility, to evaluate the act. Right? So that's for each level of awareness. And then when awareness grows, when we discover a new consequence, then now we know more consequences. So the utility function now is expanded to be defined over the larger set of consequences. But what we get out of our axioms is that the part of the utility function that only concerns the consequences that we knew before agrees with the old one, right? So I was looking for, yes, right, thank you. So, right, so if we have consequences on the first axis, utility here, and this is just a schematic drawing, right? But let's say that initially, this is the set of consequences we know before we make a discovery, and this is our utility function. And now we discover some more consequences. So these are new discoveries, new consequences, right? What the axioms give us is that the new utility function, which is red, sort of follows, agrees with the old one for the consequences we knew before, and then it will give us some utility of the newly discovered consequences as well. And the last thing we get out of our axioms is this reverse Bayesian updating of beliefs, where you see that the relative probabilities of the prior known states we knew before, the expansion of awareness is preserved when awareness grows, when awareness expands. And that also gives us that probability mass is shifted proportionately away from the prior state space to the newly discovered states. Right? So as I said early in the talk, we get the exact opposite of Bayes' rule in response to growing awareness. Okay, so I think I said all this. We extend the utility function to the larger domain, but it'll coincide with the existing utility function for the consequence we knew before. We get an expansion of the state space, and we have reverse Bayesian updating of beliefs. Okay, what about when we discover new actions? We get a very similar result. For each level of awareness, we have expected utility. Now, because we're just discovering new actions, we don't have new consequences, so the utility function in each state just remains as it was before. And here I have, so what's different is the details in how reverse Bayesian updating plays out. If you think back to our example, right, we had the prior states S1 that was described by C1, C1 is split into two states, right? C1, 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 which I call S1 hat here, and S5 hat C1, C1, C2, right? So we have an event, a non-degenerate event in the new state space that corresponds to a state in the old state space. So what reverse Bayesian updating says here is that the relative likelihood of the prior states is the same as the relative likelihood of probabilities between the corresponding events in the new state space. Right? So that's another way of, again, we're preserving these relative probabilities as awareness expands. Okay, so that was the first paper we wrote on the subject. And if you think about it, with the representation we have, right, yes, sometimes the agent gets surprised and makes a new discovery. His or her awareness grows, and we have something to say about behavior in response to that, right? We say, okay, utility, the tasters remain the same, but beliefs are updated across, according to this reverse Bayesian updating. But if you also think about it, for each level of awareness, the decision maker simply expects utility maximizer. The decision maker never takes into account that his or her awareness may expand in the future, right? So he or she always acts as if they're completely aware of all aspects of the universe. Right? But if you've made new discoveries in the past, it's reasonable that you will expect that this can also happen in the future, right? So although you cannot know exactly what it is that you are unaware of, you can be aware that there may be aspects of the universe that you cannot describe with your current language, right? So you can have awareness of unawareness. And the next step we took was to expand our framework to allow for this possibility, and again investigate the behavioral implications of that. So, so how do we do this? We say, okay, we have this list of known feasible consequences, right? But then we can define an abstract consequence, which is just none of the above, none of the consequences I have on my list right now, right? Anything else that I haven't thought about right now. And then we can, with this extended list of consequences, we can do the same construction of formulating the state space as we did before, where we exhaust all the different possibilities, now assign these extended consequences to the states, right? So what does that give us? I think I thought I would be out of time, but I think I may have, right? So if I start out with, say, as before, 2 states and 2 actions, right? Then I would define an abstract consequence to be none of the consequences in C1 and C2. I call that abstract consequence X. So now I have, when I do my construction of the state space, right, I would have, first I would have the same 4, oh, sorry, that's a 1, states as before. And then I would have, now instead of what I had C3 before, I would have an X, right? So I start to exhaust the possibilities of having one of the actions result in X, the unknown. So I have now 4 what I call fully describable states. And then I have a set of imperfectly describable states. And in each of these imperfectly describable states, I will make a new discovery. I will discover a consequence that I haven't seen before. Okay, so what do we get out of this? With the actions we impose, we get what we call a generalized expected utility function. It's generalized because it has an extra parameter, and this parameter is capturing the agent's attitude towards the unknown. So just as we can talk about an agent being risk-averse or risk-loving, we can talk about an agent being fearful towards the unknown or excited about the unknown, right? And this attitude is captured by this extra parameter in the representation. The other thing we get out of it is that the beliefs, the subjective beliefs, are now also assigning probability to making new discoveries, right? That's the probability that's assigned to the event consisting of imperfectly describable states, right? So we can also talk about the decision maker's sense of unawareness, which would be how uncertain am I about sort of the part of the world I know? How likely do I think it is that there's something I haven't taken into consideration? And we can talk about how this sense of unawareness evolves as new discoveries are made, right? So it could be increasing, decreasing, constant. Like when I make a new discovery, does it make me all of a sudden more in tune to the fact that there are things I don't know? So does it make me think, oh, I hadn't thought about that there was something out there I hadn't taken into consideration, but now that I think about it, there's a whole bunch of stuff. That would be an increasing sense of unawareness. Or it could be that I think, okay, now I made a discovery, there's less to be discovered now. So that would be a decreasing sense of unawareness. It could be that I think each discovery is very small compared to them all, so I don't really think it makes a difference on the probability of making future discoveries. That would be a constant one, right? And the last thing I want to do is to just a little bit of advertisement for the talk I'm giving tomorrow. Is in the latest paper, if you think about the first 2 papers, these 2 papers I've talked to you about, we're considering a one-shot increase in awareness. But in economics, many of the problems we're interested in, for example, in macro and finance, have a long time horizon. So what I do in the paper I'm presenting tomorrow, I'm taking this awareness of unawareness, and I'm constructing a long horizon model where we can take awareness of unawareness into account and hopefully analyze those types of problems with long time horizon and that. Okay. Thank you.
Time for a couple questions if anyone has.
Yes.
Have you looked at some empirical exercises to see if people actually behave consistently with I guess your updated expected utility?
Yeah. So I haven't done any empirical or experimental work myself. are a couple of experimental papers on basically testing that invariant risk preferences axiom. Are your preferences toward known risks constant? And sort of the first one found evidence that suggested it was not the case, but then the second paper, which was then sort of somewhat a critique of the first one in the methodology, found support of the invariant risk preferences axiom. So that's the current status of that. Thank you for your question. Other questions? Yes.
So the idea that the proportions, the probabilities are, the proportion of the probabilities is constant, is that, it just seems like new information could actually change the relative probabilities. Is that's just not allowed in the model?
When we think about problems, absolutely, right? If you think the axiom, my axioms or our axioms are appropriate, right, you would preserve the likelihoods. Also, often we're sort of going in the opposite direction, right? We want to have a model that's operational. Like one of the reasons that the expected utility model is so widely used is that it's very easy to work with because everything is linear. There are alternatives to that, like Scott has been working with some of them at least, right? But I think you can also say, right, they're a lot more complicated to work with, right? So part of it is also sort of providing, saying a result, the representation itself, like the updating rule and the representation that's easy to work with, right? And then you can also use the axiom to say sort of how much do you have to accept, like in order to work with this easy, have this representation that's easy to work with in practice. Does that make sense? Yeah. So I agree with you that you could think of situations where this would not be the case, right? For example, I mean, but it's a trade-off, right? And I'm somewhat agnostic about it. I can just say, well, if you're using this model, these are the assumptions you're implicitly making, right? If you're making these assumptions, you end up with this model. So but I think it's a useful way of evaluating, and I think it's an exercise we should always also do, even when we're working with a standard expected utility model. Are we willing to buy the implicit assumptions that we're making about behavior? Yeah.
How does this contrast with previous ways that economists have thought about expanding state spaces?
Well, they haven't really. There hasn't been much. There's been discussion in sort of the more logic side of things, which have working with sort of just the sort of definition. What does it mean to be unaware, which is not working with choices or utility functions at all. And then there were a group of papers that had looked at sort of game theory problems where they just assumed that, okay, this agent may not know some strategy of the other player or something like that. But people hadn't really, or nobody really got in and looked sort of in a choice theoretic model at these issues. So, I mean, there's a bunch of papers now, but there weren't many before. So. And so
is this, I guess this is like pretty similar to like if we were playing a simultaneous game or a repeated game, that like as you progress in the game, you become more aware that there's more options at each node.
Yeah.
Like maybe you thought there were only two options, like if you sat down, but there's actually three or four.
Yeah, I guess I forgot to go to my conclusion slide, right? So I was like, that may answer your question in the first paragraph, right? That until recently, economic models could deal well with known knowns and known unknowns, but what my research program with Adi has provided is this way of dealing with the unknown unknowns and going in the opposite direction with this expanding state space that wasn't there before. So it's something that we're very happy to have thought about. So, and I'm still really excited about it. So. That's if you are thinking about doing a PhD, choose a topic you're excited about. That's my big advice. That makes it way more fun. So.